Alright, welcome to Chapter 13 lesson for physics. This is going to be about fluid dynamics, and fluid, even though you probably think of liquid, actually pertains to both liquids and gases, so anything that can kind of flow or easily move and change shape and take the form of its container is called a fluid. So here we go, Chapter 13. In the first section we're going to be talking about pressure, gas laws, thermal expansion, and plasmas. So pressure. This is probably something you've learned before, but just simple definition, pressure is force divided by area. So it's not just how hard you're pushing, but over how much surface area that force is exerted. So if you push with the same amount of force, but one person pushes on a knife blade and the other person pushes on a big square flat book or something like that, the knife edge is going to have a lot more pressure because the area is smaller. So there's two ways to increase the pressure of something. You could increase the force, or you could decrease the surface area. So anytime you're trying to cut something, the pressure you exert is going to be higher if you have a smaller surface area, which is why sharpening a knife to a razor's edge makes it much more effective, or why stabbing someone with the pointy end of a sword is much better than smacking them with the broadside of the sword. Lower area, higher pressure. The units for pressure are actually kind of interesting. You can have force measured in newtons, that's the standard unit, and then you could have area measured in meters squared. And this is combined. Newtons per meter squared is combined into a new unit called the Pascal to honor Blaise Pascal, who was a scientist who worked on this kind of stuff. So newtons per meter squared equals pascals. Here's a simple example of blood pressure. This is the pressure that the blood inside your veins is exerting on your veins. And when your blood pressure gets too high, that's very bad because it means it's pushing outward on the edges of and you might have your blood vessel burst in an aneurysm or something like that. Bad news. Okay, new topic, gas laws. This is something that's sometimes taught in chemistry. So in an ideal world, you've already learned this in chemistry, but some of you may not have covered it, so we'll cover it right now. Any gas is going to obey the ideal gas law approximately. Some gases obey it more closely than others. Some don't obey it very closely at all. So in order for a gas to count as an ideal gas and obey the ideal gas law, the particles should be non-interacting, which means when two particles come into contact, they just bounce off each other. They don't bond together. They don't stick together. They don't exchange energies other than an elastic collision. So it's kind of like billiard balls bouncing off of each other. They should also have a low density relative to their volume. That just means that they're not all crowded together, because the more clustered and crowded that they are together, the more likely they are to interact with each other and bond rather than just bouncing apart. So very low density, non-interacting particles is called an ideal gas, but typically we'll treat all gases as ideal gases in this class because we won't be trying to cause reactions like you would in chemistry. So if you have a gas that's obeying the ideal gas law, it's going to obey this relationship. Pressure times volume equals N, which is the number of moles, times R, which is a constant, times T, which is a temperature. So let's look at the relationships that this thing tells us. Normally, the number of moles of gas, that's how much gas you have, is going to be held constant. Like say you have gas inside of a balloon. If you squeeze the balloon and change its volume or its shape, the amount of gas in the balloon won't be changing. So typically N is constant and R is always constant. R is always constant. And the units in standard units are joules, moles, and kelvins, so it's going to be 8.31 joules per mole Kelvin. So R is constant, and N is almost always constant as well. So this reduces to the three laws you've probably learned, which are Charles' laws, Boyle's law, and the Gay-Lussac law. And it's a relationship, those three laws are relationships between pressure, volume, and temperature. So something like this. If the temperature is constant, and you increase the pressure, then you decrease the volume. That's one of the laws. Or say, can I erase it? I can't erase it. Say you increase the pressure, but you keep the volume constant, then what happens to the temperature? It better go up. Or what if you keep the pressure constant and you lower the volume? Then you're going to lower the temperature. So depending on which thing you keep constant, they'll either be directly related or inversely related, where one goes up, the other goes up, or one goes up, one goes down. But the cool thing you can do is you can take this equation, which allows you to figure out all the values, pressure, volume, and temperature, for a single gas at a single point in time, and you can compare it to the same gas at some later point in time. So if you say the pressure starts at this and ends at this, what's going to happen to some of the other variables? Assuming it's a closed system, A closed system means that the number of moles is constant. That means no gas is coming in or out of your system. In this case, that's what a closed system means. It's not the same as when there's no external forces on it, or no energy transfer. It just means no particles are coming in or out of your system. I'll say that this means N equals constant. Okay, then you could divide both sides by T, and then you have PV over T equals N times R. But N times R is constant, so PV over T at the beginning, right here, should equal PV over T at the end, right here. So if you're given the initial and final values for pressure and volume, or pressure and temperature, or something like that, you can plug them in and you can solve for the unknown value. But you should always keep in the back of your head the idea that you need to know whether they're inversely or directly related, where it should make sense, like if the pressure goes up, then the volume's going to go, because there's more pressure, it's pushing that object outward, then the volume's going to expand. So always try to use your intuition to make sure that this stuff is making sense. And the second thing that's super, super, super critical, I'll put a big star right here. Temperature has to be in kelvins. Okay, anyone who doesn't believe me can try to divide by 0. A temperature of 0 degrees Celsius is totally possible, yet clearly, if you divide by 0, your pressure or your volume is not going to be going to 0 or infinity or something like that. I mean, having something at 0 degrees Celsius is no trouble. Just look at a block of ice. Okay, you can heat or cool water from ice to liquid, and there's no trouble there. But having a temperature of 0 in the Kelvin scale is technically, we can get into the minutia later, but technically impossible. So you'll never be dividing by 0 because you're measuring the temperature in kelvins. Remember what we said in the previous chapter? Anytime you have a delta T, it's okay to use Celsius, but anytime you have temperature all by itself, not a change in temperature, but the actual temperature value, it should be measured in kelvins. And the final thing to help you remember is that the units for your gas constant have kelvins in them, so that helps you remember, oh yeah, I need to convert to kelvins. Okay, let's do a little sample problem on this ideal gas law scenario to get the basics. Upon landing, a 250 meter cubed balloon, hot air balloon, cools down from 120 degrees Celsius to room temperature at 20 degrees Celsius. What is the new volume? Assume constant pressure. So we start by saying, hey, this was an ideal gas, so PV over T at the beginning equals PV over T at the end. So we start by writing that down. And then we say, okay, constant pressure. So this P1 and this P2, I can cancel them out because they're equal. They're the same value, and they show up on both sides, so I can cancel them out. And now I can look at the values that I have. It starts off 250 meters cubed, so it's very big. That makes sense, it's a hot air balloon. As it cools down, what's going to happen? It should shrink. Okay, so let's just make sure that our answer comes out less than 250. So we plug in volume 1, 250, divided by temperature 1. Well, it started off at 120 degrees Celsius. Uh-oh. That means I need to do some converting. 120 degrees Celsius equals, do you remember how to convert Celsius to Kelvin? You have to add 273. So that's going to be 393 Kelvin. Temperature 2 was 20 degrees Celsius. Add 273, and that's going to give you 293 Kelvin. So temperature 1 was 393 equals volume 2 over temperature 2, which is 293. And I actually have a calculator today. You guys would be very proud of me, I hope. So I plug in my numbers, 250 divided by 393 times 293. I multiply by 293 to get this up here on the other side. And I get 186.4. 186.4 Kelvin. No, not Kelvin. That was silly. Not Kelvin, I'm sorry. We're finding the volume, so this is going to be meters cubed, because I plugged in Kelvin and Kelvin right here and right here. Kelvin, Kelvin, and this was meters cubed. So my final answer is 186.4 meters cubed. Let's see if that makes sense. The temperature cooled down by approximately 25%, so the volume is going to decrease by approximately 25%. The more that the thing cools down, the particles are, remember, temperature is a measure of the internal kinetic energy, the random molecular kinetic energy of these particles, so how much they have on average. If they're buzzing around a little bit less, they're not going to be colliding with the walls of the balloon with such velocity and therefore there won't be as much force outward on the walls of the balloon, and the walls of the balloon will kind of gradually come in. Cool. Here we go. Next topic. I know there's a lot of disjointed topics here, so I hope it's okay. It doesn't necessarily build on itself as much in this section as it will in the future. Thermal expansion and plasmas. Okay, so you may have already learned just through your daily experience putting something in the freezer. Say you take an Arrowhead water bottle like this, you fill it all the way to the top, you put the cap on, and you stick it in the freezer. Actually, I encourage all of you to try this. If you have never done that, it's kind of cool looking. But what happens is it kind of explodes or bursts. It won't explode like blow up, but it should force the cap off the top, maybe crack the bottle. As it freezes, the water will actually expand. Now, this is an exception, actually. Normally, when you cool something off, since there's less vibrations of all the particles, that's what temperature is after all, there's less vibrations, the object will start to shrink, okay? And even with solids, that's what normally happens. As objects heat up, thermal energy increases. That means they're vibrating more and they expand, and as you cool them down, they should shrink. So the fact that water expands when it freezes is a very much an exception to the rule, which causes ice to float, which causes all sorts of, well, not all sorts of things, but imagine if you had a lake, and instead of the ice floating to the top when it got cold and froze a little bit, it all sank to the bottom. So the top layer would freeze and sink to the bottom. The next layer would freeze and sink to the bottom, and pretty soon the lake would just freeze from the bottom up until it was entirely solid frozen block of ice. And if that were to happen, there would be no way that the fish could survive through the winter. However, since whenever any of the water freezes, it floats to the top, it forms a layer of ice on the top, which insulates and protects the water that's below, which allows there to maintain a liquid environment throughout the cold winters, which allows life to stay through the winter in the lake. Okay, so normally, what do we say? Normally, when you cool something down, it will shrink, and when you heat it up, it will expand. This picture is a nice example of that. So if you've ever seen a railroad track, you might notice that every so often there's a little gap between the two adjoining pieces of metal railroad rail. The reason that they have those is because when it gets hot, the actual railroad rail itself will expand, and if you put them right up against each other and then they try to expand, there's nowhere for them to expand into. They'll push into each other. If you take two things and push into each other, they'll typically bow up like this, or they'll bow out like that. So this railroad track here is showing a good example. When they expand, they go like that. They have to get longer, and the only way to get longer is to become a curve instead of a straight line, because the straight line is the shortest path that the track can have. So if you build a railroad track and it heats up and you haven't taken that into consideration, you're going to get some effect like this. Nice and curvy. And this looks like a real photo, but to be honest, I don't know if it is, because this phenomenon, scientific phenomenon, was well documented and known before we were building railroads. So I suspect that the engineers should have known better, and maybe they mismeasured the temperature though, or something like that. Okay. Final thing in this slide is plasmas. Okay. A plasma is a fourth state of matter. You can talk about solids, liquids, and gases, which we've done in the previous chapter, looking at phase transitions. But you can ask, okay, what happens when you take a gas and you keep heating it up? Does it just stay as a really hot gas? The particles are flying around faster and faster. Each individual atom is gaining more and more energy. So what happens eventually is there's enough energy to rip the atom apart. And you're not ripping it completely apart, but there is enough to rip off an electron, or maybe two electrons, from the outer shell of that atom. So when you superheat a gas, it'll become ionized. Okay, this word ionized means electrons have been removed. So it becomes an ion. Think back to your chemistry lessons. When you remove an electron, it becomes an ion, which is a positively or negatively charged object. So now you've got a free-floating electron, which is negatively charged, and you've got a leftover ionized particle, which has a positive charge, because since it removed an electron, what's left behind is slightly positive. So some examples of plasmas from daily life are lightning bolts, neon signs, stars, fluorescent bulbs, etc. So there are actually quite a few examples, and as you might imagine, all of these examples deal with something that is very, 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 very hot. So plasmas only occur when you superheat something like a gas, and it causes it to ionize. Okay, I just want to make explicit in your book if you're reading the chapters, which I encourage all of you to, recommend it highly. They do have equations for thermal expansion of different things, and we're not going to use those at all in this class. I've decided we're just going to learn thermal expansion as a concept. So whether you're math or concept, you definitely still need to know the idea of thermal expansion, when it occurs, why it occurs, and what the main exception is, which is water being the main exception, and why that's important. Okay, forces within liquids. Okay, so now let's zoom in on liquids and ask ourselves, how do these liquids operate? So here's some examples. We're going to go through these vocabulary words: adhesion, cohesion, viscosity, evaporation, condensation. And we can talk briefly about evaporative cooling and how that works. It's a very useful phenomenon. Cohesion. Cohesion, as the name suggests, co means together. Not doesn't mean together, but what does co mean? Cohabitate, coexist. I guess it means together. Anyway, it's the forces within a substance that attract the molecules to each other. So anytime you're talking about cohesion, you're talking about two molecules of the same type attracting each other. So when you look at water droplets, like this picture suggests, you might pour water onto a surface and you notice that the water clumps together. That's because of cohesion. The water molecules are attracted to other water molecules and they'll group or cluster together. Okay? Adhesion, on the other hand, adhesion refers to attracting to something different than yourself. So when a water molecule attracts to the glass in a beaker, causing a meniscus on the edge. So all the water is attracted to this glass wall, causing it to raise up a little bit from its level value. That's because of adhesion. So the molecules of one substance are attracting to external molecules of a different substance. So if you've heard of capillary action, maybe from your biology classes, where water can climb up a small tube, or when you look at the meniscus of a liquid in a cylinder, those are both examples of adhesion. I'm sure you could think of many more. Some more vocabulary words. Viscosity. If you've ever baked with molasses, you definitely know what viscosity means. Well, you definitely have seen examples of it. You may not know what it means. So viscosity is the slowing of a fluid flow based on internal friction and intermolecular forces. Okay, so when you try to pour a fluid out, does it flow out very, very easily, or does it flow very slowly like molasses? The reason that fluid might flow more slowly is because there could be a lot of friction between the molecules. In order for a fluid to flow, those particles have to slide past one another. If there's a lot of friction, they won't be able to slide past as easily. Second thing is, we just talked about cohesion. They're bonded to each other, and adhesion, they're bonded to the walls of the container. The stronger the cohesion and the stronger the adhesion, the more they're going to bond to each other, and the less easily they're going to fall away from their particles. So if you have high cohesion, high adhesion, you're going to have a higher viscosity. Okay, evaporation and condensation are in here simply because they're part of the chapter, but I trust that you guys already know what those are. So pause it and read it if you don't, but it should be quite obvious. Break time, but let me talk about evaporative cooling. So evaporative cooling has to do with evaporation and the way that it extracts energy from something. So when you sweat, you've got this liquid water all over your skin, right? In order for it to evaporate, the most energetic particles escape from the liquid phase into the gas phase. So let me draw a little picture here. So here's your skin. And here's, some beads of sweat. Okay, now if we zoom in on this guy, make a little magnifying glass. So we zoom in on that guy. If we look at the energy of all those little particles in there, they kind of form, if we look at the energy, and then we look at the number of particles, oh, I got those backwards. Sorry. The number of particles and energy. I apologize. It makes what's called a bell-shaped curve, which means right in the middle, you've got lots and lots of particles that have kind of an average or middle amount of energy. You've got a few particles that have low energy, which means they're not moving very fast, and you have a few particles that have a lot of energy, which means they're moving very, very rapidly. So these guys right here are the ones that escape. Okay, so your body is hot. Okay, it provides energy into this sweat molecule, which makes these little guys, all these little sweat molecules, gain energy. Some of them will be moving fast enough, the fastest ones or the hottest ones, will be going so fast they can burst out of the surface of that sweat bubble and escape into the sky as a little, basically vaporized water, water vapor. And what that does then, if you look at the total energy of all of your guys that you have left, it's decreased, okay? Not only has the total energy decreased, but the average energy is decreased because you extracted one of the biggest guys. So the average value, think about a room full of people. If you look at the average height, and then you take away the 5 tallest people, the new average height is obviously going to be lower. So you take away the most energetic particles, the average energy of all the rest is going to decrease, and therefore the temperature is going to decrease. So when you sweat, it allows the most energetic particles to escape, which then cools off what's left over. And this cycle just keeps happening. Your skin is warming up the sweat, the most energetic particles keep leaving, and that cools you down. So, the only way that these particles can gain energy to escape is by extracting it from your skin, which therefore cools you off. So evaporative cooling is useful in human sweating. It's also why dogs pant. They've got liquid on their tongue. When they breathe in and out rapidly, it's blowing new air over the surface of the tongue. Why would it be bad to not pant? Okay, let me talk about that a little bit. Or when you're sweating, why is moving your arms rapidly back and forth or blowing a fan on you, why does that make you feel so much cooler? Well, if you have no motion, if you're just standing there totally stationary and you sweat, what happens is a couple of the molecules will evaporate or escape, but they'll just stay right there above your skin. And pretty soon, the area right above your skin is now saturated with evaporated particles. Have you guys heard of partial pressure or vapor pressure of a gas, or above a liquid of gas whatever. Maybe you have, maybe you haven't. In any event, you can imagine that if a whole bunch of sweat particles have evaporated and they're all hovering right above your skin, it's going to be a little bit harder for new particles to evaporate and join them because there's already some particles taking up that space. But if you have a fan blowing on you, every time one of these particles escapes, it gets blown away. And so there's constantly an open available space for these sweat particles to evaporate into. Another link to this idea is that on a muggy, humid day, the air is already saturated with moisture, and it's harder for your sweat to evaporate, which is why you sweat a lot, and it feels like, oh my god, I'm just coated in sweat. It's because the sweat can't evaporate because there's nowhere for it to evaporate into. The air is already saturated with water molecules in the water vapor phase. On a very dry day, you can have your sweat evaporate really, really, really easily, and therefore, even though you may be exerting a lot of energy and heating your body up, the sweat will continue to evaporate and therefore extract energy at a more rapid pace. Okay, I put break time, so let's take a small break. Let your mind rest, let your hand rest, and then come back to this in a few moments. All right, welcome back from your little short break. Hope you had a snack. Let your mind rest, go do something fun. We're going to finish off with the last 2 sections of Chapter 13. Chapter 13.3 is about fluids at rest and in motion. This is the most mathematical chapter. It's the most robust. It builds upon itself, and it's going to yield a lot of problems that we can solve. So it deals with Pascal's Principle, hydraulics, pressure underwater, which leads to buoyancy and Archimedes' Principle, and then finally lift and Bernoullis Principle, how airplanes are able to fly, etc., etc. So we'll start off simple, Pascal's Principle. Pascal's Principle, which you should memorize, is that for a given depth, the pressure in a fluid is constant. Okay, so this is a main application in hydraulics and lifts and that kind of stuff. I'll draw a picture in a second, but if you just accept that the pressure is constant, then we can get a cool formula for hydraulic lifts. The pressure at the beginning on one side of the lift is equal to the force on that side divided by the area on that side. The pressure on the other side of the lift is equal to the force at the second position and the area at the second position. But these two pressures have to be equal. So if we substitute in force over area 1 for pressure 1 and force over area 2 for pressure 2, okay, we get this equation that the force exerted on the second piston, if you will, is equal to the force exerted on the first piston times the ratio of the areas. Well, if the area of the second piston is, say, twice as big as the area of the first piston, then that's going to yield twice as much force. So that seems reasonable. You've got a liquid, and it's pressing up against the piston. If the piston is bigger, that's going to be a bigger force because you're pressing the same amount on a bigger area. So now you might be asking, oh, is this some kind of magic? Let's draw a little picture. So here's a little piston, and it connects to a bigger one. Okay. Okay, so say this whole thing is filled with fluid, and right here my area equals 10, and over here my area is 100. A1. And say I press with a force. Force equals, I don't know, 50 newtons, something like that, okay? So then the pressure exerted on this right here, pressure is the force over the area, which is 50 newtons per 10, let's say, meters squared. I should give you units. Be a good teacher. 110 meters squared. Okay, so that's the pressure exerted here on this side. Okay, that pressure is going to be transmitted through the fluid, so that all the fluid in this entire thing, say this is solid full of fluid, all the fluid in this entire thing is experiencing that pressure. It's getting pushed, okay? So you push it forward on this piston, it's going to push this fluid through here, push the fluid through here, and there's going to be a force then on this side. Okay, and let's look at that force. Force 2, remember pressure is force over area, so force is pressure times area, which is 50 newtons over 10 meters squared. That right there was our pressure, times 100 meters squared. And again, this matches the same formula. I'm going to go back. This formula right here, the force exerted outward equals the force exerted inward times the ratio of the areas. So this right here is the ratio of the areas. So the force 2, it's 10 times bigger, because 100 divided by 10 is 10. It's 10 times bigger. It's going to be 500 newtons. So you might ask yourself, what is going on? How can I push with only 50 newtons here and get a force of 500 newtons here? I mean, when this piston moves a certain distance, this piston is going to move. If I'm exerting 10 times more force, aren't I going to be doing a lot more work? Isn't more work going to get done here than get done over here? Aha! And now you can ask yourself, is it possible to get more work out than you put in? Hopefully you've all agreed that the answer is no. So let's look a little more closely at the work done. Do I have a slide for this? No, I'll do it here. Aha, picture discussion of work, force, and pressure. The pressure everywhere is the same, but the force is much bigger over here, so let's look at the work. Work equals force times distance times cosine of the angle. But in this case, everything is getting pushed perpendicular, it's getting pushed parallel to the way it's moving. The force, we can say, is inward, and the piston is moving inward. So the cosine of the angle isn't going to matter. So let's zoom in on force and distance. Certainly the force over here is 10 times bigger. So now let's look at the distance. If I push this guy, say 2 centimeters, look at the volume of fluid that's going to be. How much volume of fluid is that? Well, it's the surface area times the length that I push it. That will give me volume. Area times basically height of this cylinder is volume. Now look over here. How far is this one going to move? Okay. The cross-sectional area is 10 times bigger. So that fluid that I pushed, it's going to expand and it's going to spread out to cover that entire plate, that entire surface area, which means the layer is going to be a lot thinner. So over here, if it was 2 centimeters, over here, it had to cover 10 times more area, so it's only going to be 1/10 as thick. Okay, so the force is 10 times bigger, but the distance that this piston actually moves is only 1/10 as big. I'm putting x just as a variable. So the result of that is that the 10 and the 1/10 cancel out, and you get the same amount out as you put in. Okay. You have a bigger distance, but a smaller force. Over here, you have a bigger force, but a smaller distance. And they perfectly balance out so that the work done by you pushing this side is exactly equal to the work done over here by this side of the piston pushing whatever it's pushing on, of course neglecting friction. Okay, so we still conserve work and energy, but the force increases because the area increased, and pressure was constant. Cool. Okay, pressure underwater and the buoyant force. So we just said that pressure is constant in a fluid, and now you might be saying, what the hell? Now Morgan's saying pressure underwater gets bigger the deeper you go. But remember, our caveat for the first one was pressure is constant at a given depth. So if you've got some kind of cylinder lying on its side, basically all of this is at the same depth, so all of it will have the same pressure. That's a lot different than swimming 50 feet under the ocean. And the reason is because the pressure is caused by the weight of everything above pushing down on you. So the deeper you go, the more water there is above you pushing down, and therefore more pressure. So the formula is pressure, capital P, equals, this symbol right here is called rho. It's a Greek letter R-H-O, rho. And you kind of draw it like this. Start right here, make like a P and kind of swiggle backward, like that. These are all excellent rows. Row, 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 row. Your boat gently down the stream, of course. H is the depth underwater, or the height of water above you. And G, as long as you're on Earth's surface, you should be using the acceleration of gravity on Earth's surface. If you're doing a buoyancy or an underwater experiment on some other planet, you should be using the value of gravity on that planet's surface. Okay, so the pressure is equal to the density of the water times the depth you've pushed it underwater times the acceleration of gravity at the location where you are. So this tells you something you already know, that when you go diving underwater, the farther down that you go, the more pressure there is pushing in on you, which is why, you know, submarines have to be built to be super, super strong, otherwise they'll get scrunched. That's why when you go swimming, if you swim down to the deep end, your ears hurt more. That's why you need to wear, you know, scuba diving equipment, etc., etc. That's why when you, if you surface too fast, your lungs will explode, because the pressure is decreasing. Well, it's increasing as you go down. Therefore, when you come back up, the pressure is decreasing. As the pressure decreases, according to the gas law, what happens to the volume? It expands and increases, and you'll have all of your cells with oxygen explode on a cellular level. We can talk about that in class as well. Okay, so the pressure increases as you go deeper. That causes an interesting phenomenon called buoyant force. Okay, so we're going to zoom in on this in a lot more detail. The buoyant force, the formula here is the density times the volume times gravity, and you've probably heard this expression, I think it's called Archimedes Principle. There will be an upward force on an object equal to the amount of the weight of the water that it displaces. So the more water that your object displaces, the more the upward force is. But I want to approach it from a more physics standpoint, which is looking at the difference in pressure on the bottom and the top. So say you've got an object submersed. The pressure on the top is going to be a certain value based on how deep it is. So say this is the depth underwater. Say here's the surface of our water. So there's your pressure on the top. Now the bottom is deeper. So the pressure on the bottom is going to be higher than the pressure on the top. So you've got pressure pushing down on the top and pressure pushing up on the bottom. But since they're at different heights, they're going to have different values. And the one that's deeper, the bottom, will have a higher pressure. So the force upward on the bottom is going to be bigger than the force downward on the top. And the net result of that, the difference in those two forces, provides a net upward force. Okay, side to side, they balance out because this top little edge here is balanced out. So you can kind of think of it as a layer of really thin pancakes. Each one has a balanced pressure left and right. So as you go down, the bottom pancakes have more pressure on both the left and the right side, but they're still balanced with each other. Left is balanced to the right, all the way up. So these arrows demonstrate nicely. As you go down, the pressure increases, yet it's increasing at a balanced level. Yet the bottom and the top are not balanced, and therefore there's a net upward force. So the buoyant force is the net overall effect of all of these force arrows combined on a object based on the pressure exerted on the different sides of it. Okay, so let's look at the formula. It depends on the density of the water. Density of the water. The reason it depends on the density of the water is because the pressure depends on the density of the water. The farther down you go, the more the pressure, but also the denser the fluid, the more pressure there's going to be. Second thing is it depends on the volume of your object. Well, if you have a bigger volume, right? One thing is the bottom and the top will have a larger distance between them, which means the difference in pressure will be higher, which means there'll be a bigger force. Also, the bigger the surface on top is, the more force there'll be, because at a given pressure, if you increase the surface area, you increase the force. So the force will depend on volume, because the more surface area you have, the more force there is, and also the bigger the distance between the top and the bottom is, the more upward force there will be. And again, the acceleration of gravity, this is again because it depends on the pressure. The more force of gravity there is, or sorry, the more acceleration of gravity there is, the more pressure there will be, and the more pressure there will be, the difference in pressure between top and bottom is what causes this in the first place. Okay, I've got a little note to myself to discuss apparent weight. So apparent weight is your actual weight minus whatever is suspending or keeping you up, which in this case is the buoyant force. So say you weigh 150 pounds, and then you jump into a pool, and you feel almost weightless. Maybe you even float. Your apparent weight is drastically reduced because you've got this upward force on you. So I have space here, I'll do it in the corner. Your apparent weight is your actual weight, which is the force of gravity, and there's your F buoyancy force holding you up. Your apparent weight is the difference between these two. If the buoyant force is bigger than your force of gravity, then your apparent weight is negative and you'll actually rise up into the air. If your buoyant force is a little bit less than your force of gravity, you'll still sink, but with much less force than you would have, and much less acceleration than you would have if you were in free fall. So again, your apparent weight is how much it feels like you were weighing when you take into consideration both of these forces. Okay, so now I'm going to go into an alternate way of thinking of this buoyant force. So here we go. Think of pressure as the weight of the water above you. Okay, so if you're standing here underwater, and then here's the surface of the water, you've got basically a big rectangular pile of water above you. Okay, let's look at the weight of this water. We've got force is mass times gravity. To find the mass of this water, we need to relate the density. Density is mass divided by volume, right? So therefore, mass is density times volume. Okay, so plug that in right here, and you get that the force of gravity on this stuff is the density of it times the volume of it times gravity. So that's the force acting on all of this stuff, pushing it down on you. Okay, so to find the pressure on you, you have to do force divided by area. Okay, well, force divided by area is going to be the density times the volume times the gravity divided by your area. Now the volume divided by the area, we've got the height. So there's a way to get the formula for pressure by looking at the weight of the water above you. Let me zoom in here. Volume divided by area equals height. Let me show you why. Suppose you've got a cylinder. The volume of a cylinder is the height times the area. So if you divide both sides by area, it works for a rectangle or a cylinder, doesn't matter. Areas cancel, and the height equals the volume divided by the area. So V over A equals H. Cool. Second thing, derivation of the buoyant equation for a cube, an extension to any object. So if you have a perfect cube, let's draw that guy. Okay, you've got a height and you've got an area here, and the pressure at the top. Okay, and you've got some distance. Okay, let me do better here. The distance here we're going to call d1, and the distance all the way to the bottom we're going to call d2, and the height of the object is going to be d2 minus d1. If you're not comfortable, if you're not in the math section, you can skip this completely. If you're in math, you should probably pay attention. Pressure on the top is going to be the density of water times d1, the depth at the top, times gravity, and the pressure at the bottom is going to be density times d2 times gravity. And now therefore the force on the, let me just go up here. The force on the top, it's kind of like what we're doing up here. The force is pressure times area. So we have to take this pressure and multiply it by the area. So we just said if you multiply the distance times the area, If you multiply the height times the area, you're going to get the volume. So that's going to be pressure times, I guess I'll do it this way, d1 g times the surface area of the top, and the force on the bottom, I'm sorry, this is kind of messy. Force on the bottom is density times the depth number 2 times gravity times the area. So here's my force on the bottom pushing up. Here's my force on the top pushing down. Okay, I need to subtract these two to get the net force upward. Okay, so if I subtract these two, I can factor out what they have in common. They both have a rho, they both have a g, and they both have an a. So the F net is going to be rho, g, a, and then what's left behind is d2 minus d1. But d1 minus d2 is just the height of my object, and the area of my object multiplied by the height of my object is the volume of my object. So I've got the density of the fluid times the volume of my object times gravity. And that right there is what we said the formula was for the upward buoyant force on the object. Okay, so by looking at this formula for pressure underwater, and by looking at a super perfect square object, we can prove this formula very easily. So I hope you're convinced that this formula is true. But you might say, well, this is stupid. This only works for a square, right? Like, what if it's some weird oblong-shaped object? So now I want you to think about, if you're in calculus, think about the limit, as the object is made up of a bunch of squares. But even if you're not, if you're at all interested in photography, or you know about computers and pixels, imagine you take some weird shaped object. So instead of a square, we've got some weird shaped object like this. If you zoom in far enough, this object will start to become pixelated. And you could think of it as made up of millions and billions and billions of tiny little cubes. And each one of those cubes obeys what we just said. The force on each one of those cubes is going to be given by this. And if you sum up or add up all of those little cubes, it'll give you the overall net object, and the net force, the sum of vectors all pointing in the same direction. All of those forces are going to be upward on each little cube. The sum of all those will give you the net overall force. And so the density doesn't change, and gravity doesn't change. So the only thing that's changing is the volume of the object. If you break an object into 5 billion little cubes, and you add them all up, it's going to give you the total volume of the object. And therefore, this works for any shape object. If that didn't make sense, ask in class, and I promise I can do a better job of explaining it. So again, these are just two different ways to visualize the pressure underwater and the buoyant force. Since here I'm just giving you the formula, I want you to really understand where they come from and why they are the way that they are. It's not just some magic that we found out. It's very intuitive, based on the idea that the deeper you go, the more pressure there is, because there's all this water above you pushing down on you. Okay, demo and examples is things we can do in class, or at home. Try pushing stuff underwater. Try taking a water bottle, have it full, push underwater, and gradually drink some more and more and more and more and more water. And each time you drink a sip, push underwater, and feel that the more you drink, the volume is staying the same, but the weight is decreasing, and therefore you're going to have to push harder and harder and harder to submerge it. Maybe you could take data, find the force needed to push it, and then plot a graph of that. That'd be super cool. When you do calculations like this, you should always draw a picture and label your forces. So we're right back to doing force diagrams. So you might have, some water here, and you might have your object here, and you're going to have force of gravity downward. And now if it's underwater, you're going to have force buoyancy upward. That's the minimum you'll have. You might also have things happening to it. Maybe, someone's pushing it down, or someone's pulling it up, or maybe it's a fish and it's on a fish hook, so there's a force upward from the fish hook. But at the minimum, you're going to have the buoyant force and the force of gravity on any object that's submerged, and then add other forces as necessary. And then, F net equals ma. Plug in all of the forces in your force diagram into F net, where up is positive and down is negative, just like you've been doing before. So force diagrams are always coming back to catch up with us. Shortcut. Every year, I think it's useful to have you guys discover these shortcuts yourselves, but then I forget to go over them. So I'm going to talk about it right now, and then I want you to be on the lookout for it. If you've got some object that's floating in water and it's exactly 50% above water, and 50% below water, you can tell something cool about it. You can tell that the density of your object is exactly 1/2 the density of water. And the way that you can tell that is as follows. The force downward is mg, right? This is the actual mass of the object. Okay? The mass of any object is equal to the density of the object times the volume of the object. Okay? The mass of any object is the density of the object times the volume of the object. Then you've got the force buoyancy upward, and that's equal to the density of water times the volume of water displaced, which is only 1/2 the volume of the object, times gravity. Okay? And then these two have to be equal because your object is floating. It's in equilibrium. It's not rising, it's not falling. The upward force and the downward force have to be equal. Let me draw in here F. Boy. So if in order for this force right here to be equal to this force right here, you can immediately see that the density of the object is 1/2 the density of water because it's halfway submerged. Okay? So the more submerged your object is, the closer its density is to water. What if your object was 20% up here and 80% down here? Okay, then the density of your object is 0.8, or 80 out of 100, times the density of water. If your object is completely submerged, but still floating, then it's exactly equal to the density of water. And if your object starts to sink, you know it's more dense than water, but you can't tell how much more dense unless you know the acceleration that it's sinking with. But I just want to remind you that there's lots of ways you can combine the mathematics of this chapter to kind of come up with shortcuts like this. So keep that in the back of your mind. Finally, Bernoullis Principle, and then one slide after this, and then we're almost finished. Bernoullis Principle is actually really cool. It's how things fly, in the most part, how airplanes fly. Not things that flap their wing, but anything with a solid fixed body wing with air flowing over the tops and bottoms. So it's a cool phenomenon. Bernoullis Principle is just the phenomenon that when the velocity of a fluid increases, the pressure exerted by the fluid decreases. In class we can talk about some reasons why that's the case. I have some ideas, but I'm not sure if it's ever been kind of documented why. It's just a phenomenon of nature, and we can talk about it more in class. So the faster the gases or liquids are moving, the less pressure they're able to exert. Okay? So as a demo, you can blow on a piece of paper. Let me get a piece of paper and show you. So if you take a piece of paper like this, hold the two ends gently. Hold it so it's kind of falling off to the side like this, and then blow, put it right under your bottom lip, and blow over the top of it. Let's see if this works. Okay, so I'm actually blowing above the piece of paper. So you might think that that should blow the paper down, but if you blow just above the top of the paper, so the paper is kind of falling off like this, and you blow air out this way, the moving air right here has less pressure than the air down here. So the air down here is still, the air up here is moving, so the force upward from the pressure here and the force downward, they were balanced when there's no motion of air, but now that you're blowing the air, the pressure here decreases, which means the net force is upward like this, and it tends to lift the paper up because the air on top is not moving as fast as the air on the bottom, so there's less pressure, so there's this upward force that provides lift on the piece of paper or lift on an airplane wing. So in order to have this upward force, you need the air on top to be moving faster than the air on the bottom. Well, clearly you can't have a bunch of little people standing here on the airplane blowing air over the top of the wing. You know, it's not going to work because they're too small. Now, if you had a really big person, this might work. But in general, you need a way for the air on top to be moving faster than the air on the bottom. Okay? And the shape of the wing is how that engineers have chosen to achieve this. Since the wing is nearly flat on the bottom and curved on the top, the distance the air has to travel to get from the front of the wing to the back of the wing over the top is slightly longer than the distance it has to travel under the bottom. So assuming it's going to get there in the same amount of time, whether it goes over or under, it's going to have to travel a bit faster if it goes over the top than if it goes under the bottom. and therefore, since it's moving faster, there's going to be less pressure. I should put in the word less right here. Less pressure exerted by faster moving air on top, and more pressure exerted by the slower moving air on the bottom, and then net force therefore on the bottom is higher and upward. Okay, so now you might say, well, that's kind of a big assumption, Morgan. How do we know that the air is going to get here in the same amount of time? And the answer to that is, ask yourself, what would happen if the air did not get there in the same amount of time? What if the air moved with the same speed on the top and the bottom? When this particle made all the way over to here, this particle right here might only make it to here. Say that was the same distance, because it's curved, it doesn't go as far. What that does is it creates a giant vacuum right here. Okay, this is going to have low pressure because there's no air particles here. This particle here, it hasn't got there yet, so there's a big empty space here. Well, if there's low pressure right there, the air is going to kind of flow into it. So lower pressure here is going to almost suck this air over faster. And so the air on top will be moving faster to fill that void. If it didn't move faster already, it's immediately going to get sucked over there, and which is going to cause it to move faster. So the air will move faster on the top, thereby creating less pressure here and more pressure on the bottom overall, which creates lift. A second example of this is a little spray perfume bottle. You've got the tube going down into the perfume, and then when you squeeze this, it makes air pass through the tube. Okay, the air is passing over the top of the straw that extends down into the perfume. That air passing over the top has motion and therefore less pressure. So there's the pressure on the fluid pushing it up here is higher than the pressure up here, and therefore the fluid will move up the thing, hit the column of air, and get pushed out like that. Kind of cool. So Bernoullis Principle is simply about the relationship between the velocity of the fluid and the pressure exerted, and then the natural consequence of that is that airplanes fly, perfume bottles work, and I'm sure you can think of many other examples. Alright, very last slide. This is again concept only, so even if you're in, when I say concepts only, I don't mean that the math people don't have to know it, I just mean that we're not going to use any equations. So we've been talking a lot about fluids, gases and liquids, but we have not spent much time talking about solids. And so briefly we're going to mention the types of solids, but we're not going to go into very much detail on them. Crystal lattice solids are any solids that are formed by a periodic molecular structure. So some examples of what their crystalline structure looks like would be this, and would be this. So some examples are like sodium chloride. The atoms are arranged in a very structured way, and you can tell because when they break along nice straight lines. They cleave very nicely. The other type that we could have is called an amorphous solid. So amorphous means basically without shape, no definite shape. So an amorphous solid is still solid, it doesn't flow, but its shape is more malleable. So an example of that would be like candle wax or maybe glass. These things, they're a lot more malleable. They don't break in nice, clear, defined patterns. Their atomic structure, if you were to look at it, looks something like this. The atoms are still bonded together, obviously, but they don't have a nice crystal lattice structure where everything is ordered and regular. It looks a lot more random, and you can imagine bending this a little bit. This one you can imagine bending a little bit and having it still be a solid. Whereas this one, if you try to bend it, what's going to happen is pretty much it's going to break. Elasticity then is a property that determines how well a solid can return to its original shape. So if you have a crystal structure like this, if you bend it a little bit and then you let go, it might return. But if you bend it very much, it's probably going to break. So it's probably not very elastic. On the other hand, if you've got an amorphous solid, you might be able to bend this quite a bit and have it return back to its original shape. So elasticity depends on how easily an object can be bent and then returned to its original shape. And elastic waistbands and pants are an example of something that is very elastic, hence the name. So with this solids, the two types of solids, and then this vocabulary word elasticity, that's pretty much all you need to know for now about solids. But if you have a lot of questions or something like that, I'm happy to talk about them in class. All right, that's it for chapter 13. I want you to make sure you focus on the concepts for everything and the mathematics. Zoom in particularly strongly on the buoyant force and pressure underwater and how that leads to buoyant forces, because we can tie this back into force diagrams and what we've already learned in previous chapters. All right, I look forward to talking about this stuff in class. What up, Tracy?